Hi, so this is going to be the homework one part A. What we have is three gravity tanks, and essentially what's happening is there's water and they're flowing through the tanks for a certain amount of time. What we do know is they're also at steady state, and we're going to be using Colab to help solve our derivations and whatnot. So let me just start by modeling this problem. So one thing to note, these tanks are of like same proportion and size and whatnot. So even though it doesn't look like it, it's same. So we have this drainage hole emptying into this tank, and this one going into this tank. We have another one exiting. So let's label in terms of variables. So we have the inlet flow, the outlet flow for the first tank, but the inlet for the second tank. Q2, and then Q3, and then we have the heights of the a little too far, but the heights of the liquid or water in each tank, and because we know that the tanks are of the same proportion, they're going to have the same cross-sectional area. So I'm going to label that as A, A, and then same area for the drainage hole for all three tanks. Again, doesn't look like it, but it is. Then we're going to start with what. So what's the first thing we know about these tanks? They're going to have a certain volume, and what essentially the volume is the area times the height, the cross-sectional area in this scenario by the height. And since we're taking this in terms of rate, we're going to derive this in respect of time, the ratio of height with respect to time multiplied by the cross-sectional area. And what this is essentially going to equal is the reason as to why there's a change in flow. It's because, or change in volume is because of the change in flow rate. So it's going to be the inlet minus the outlet flow rate. And then we're just going to be looking at this section right here. So it's going to be dH dt equals, I'm going to move that cross-sectional area over, the inlet minus the outlet. But what we do want to know is this outlet, and how we can figure that out is with the Bernoulli's equation. And essentially what we're doing is we're relating the pressure to the height to the velocity. So let's just start by writing out the equation we're going to be using. So we'll use a different color. So P2 minus P1 over density plus the gravity times the difference between the 2 points that we pick, which I'll show in a second, and then our velocity equation, which is 2, and then typically this is going to have our like friction, viscous losses and whatnot, but for the sake of simplicity we're going to count that as 0, and it's not really stated much in the problem, but usually we would have this. However, we're not counting it in this problem. And I'm going to start with this section because it kind of relates to what I want to explain for this. We're going to be picking 2 points here, which is going to be 1, and then here which is going to be 2. And essentially what we're relating is the top of the liquid to the drainage hole or the bottom, and this is going to be our height. So this Z1 that we see here and Z2, this is going to be the height. However, we notice that it's the bottom minus the top, which is kind of saying like you're doing 1 minus 2. So it's going to be negative, and this will pan out later on in the governing equation. And for this, because those 2 points that we picked, you can kind of see that they're both exposed to the atmosphere. So in terms of pressure, they will be the same. So P1 will essentially be equal to P2. So this will be 0. And then for velocity, what we're looking at is the outlet flow. And I can also just write down what Q out would be. It's the area or cross-sectional area of the drainage hole multiplied by the outlet velocity, or the velocity, but in terms of the outlet, it's going to be the second velocity that we see. And we're going to count this as negligible or 0. And essentially why we're also saying that is because if we look at the area, cross-sectional area between the tank and the drainage hole, what we're saying is basically when the inlet flow is going into this tank, this area is a lot larger than this, so the velocity going out here is going to be significantly higher, as there's just a smaller area for that to go through. And with this being squared as well, it's like this number is going to be significantly less than this, so this counts as just negligible. And essentially what our final equation will look like will be g times negative h plus v2 squared over 2. And if we do the algebra to this, this will just pan out to be 2gh. And if you see our equation right here, we're going to be plugging in for that q out, So dh over dt will equal 1 over the cross-sectional area times the inlet minus the actually first we're gonna plug it into this. I forgot it's not V2 that we're looking at. We're looking at the times 2GH. So this will be the area of the drainage hole times 2GH. And since we're also saying that this system is in steady state, this dH over dt, that's bad, is going to be equal to 0. So when we do that, we're going to get 0 equals 1 over A, which equals just, or multiplied by the inlet times, or minus the drainage hole times square root of 2GH. Essentially what we're trying to do here is we're trying to isolate the dependent variable, which is going to be this H right here. So we're just going to have to align all this stuff over this side and get this H alone. So we move this over, it's just going to be 0. So then we're going to have 0 equals Q in minus area of drainage hole times 2GH. Then what I will do from here is just make it so that it's this 2GH equals Q in, and then we're going to have this be square root of 2GH. Oh, my bad. Over AH, and then H is essentially just going to be it's going to be Q in squared, and then just going to be divided by 2G. I hope I got that right. Now square divide. Yep. So this is essentially what we're going to be solving for in what is it, Colab. And what this h is essentially is the height at um, time equals 0, basically. Yep, and then we're going to go to the coding section of this homework. So I'll just stop recording. Hi, so I lied, I just took a little break. Before we get into the coding, I actually just want to go through what our variables and what our equations are. We're just going to list them here, and I'll have them on the side so that when we're going through the actual code, we have something to refer to. So let's get started. So what do we know? We know gravity. It's a constant, which is 9.8 meters per second squared, meters per second squared. And then we know our cross-sectional area and the drainage hole area. Cross-sectional area is 1 meter squared, and this drainage hole is 1.1 meters squared. And then we also know the inlet flow. However, I want to call this Qin naught because it is the initial at the start, rather than the Qin where we're deriving and we're looking at the rate of change. So this is going to be the initial value, which stated is meters cubed per second. And then it also states the set point, which we're going to call HSP. And in this term, we're going to call this 1.2, and it's going to multiply the initial H naught value, which, because it says it is 20% higher than initial steady state, so we're going to have this being 1.2 times the H naught. And then we have our two equations that we found earlier, which the first one will be the DHT, or DH over DT, DH over DT, which is the 1 over cross-sectional area times the inlet flow minus the drainage hole area times the square root of 2GH. And when we're looking at in terms of the 3 tanks, it's going to be the 1, 1, 2, 2, 3, 3. And then this will also change. So before I said, the inlet of the first tank, and then it goes out. So the outlet is going to be the inlet of the next tank, so on and so forth, as a little review. And then what else do we have? We have our H naught, which was the equation we just found. I'm again just calling it H naught because it is at t equals 0, which is the Qin, and we're going to use this naught value because we're again referencing the initial times divided by the area of the drainage hole squared multiplied by 1 over 2g. Oh, and then we have one more. So here it says determine computationally the maximum value for the controller gain beyond which the liquid levels become unstable. So what we're essentially looking at here for the coding section is we are utilizing this controller, and for this portion we're only using the proportional controller, not the PID or PI controller in terms of that logic. So for this, we're going to use the value KC, and I'm going to set a random value of 0.5. And essentially what we're going to be doing is we're going to, after we code this and we get our plot, we're going to manipulate this value to find just before when this liquid levels become unstable and starts to oscillate, and we want to find that perfect, or not perfect, but a good value, kind of seeing what the maximum is before it goes crazy. So yep, these are all our values, and I will pause this and then we'll get to the coding section. Alright, so this is Colab, and we're going to start with our coding now, and so let's just jump right into it. We're going to import some things, so import as and p, and then from SciPy dot integrate, and we're going to import solve IVP, and then from plotly dot subplots, we're going to import make underscore subplots. And it's just going to help us solve everything and numerically brush everything out and help us make our plot. So, yep, let's get started. So after we get our importation and all, we're gonna just write down what we know, all our variables and essential equations that we need. So let's just write it down like we discussed before. And area Q naught, which will be just 1. And then before we write down our set point, we want to define our initial height so that if we write down set point before initial, then it'll just cause an error because it's not defined before it runs through, because I did that on accident at first. And we're gonna QN, and then two times G. Then we can do our set point, which is 1.2 times B. And then we're gonna just write down our, or no, we already did that. So we're gonna do our KC value, which is 0.5, and just to recap from 30 seconds ago in this video, our KC value is essentially going to be just changing, but for now we're just going to use a random value. I've plugged out 0.5 as a baseline, and then from there we can see if we need to decrease that value or increase it. We're going to define how long our simulation is going to last, so 1,000 seconds in this scenario, and tplot will equal the lens space, and this is where NumPy helps us out. So 0, I'll explain what this means in a second. So what this is doing is we are defining at in 1,000 seconds we're going to have 0 to 1,000 points. So for each second we are having 1,000 data points. And then before I move on, let's just check what our initial and HSP points are. So 5.102 is our steady state height, and then this is HSP is basically our target. So when we look at our plot, I'll show you here in a bit, but this is what we're hopefully gonna achieve. And then we're going to define our right-hand side, which is time and vector. I don't like that space. And basically our vector is our heights, as I mentioned. So and then we're going to move on to our outlet flow rates, which is essentially just this portion right here. So if you remember that, it's like 2 minutes ago. Square root 2 times G. Except this one, since we're doing for 3 outlets, we're gonna have 3 equations, and the only difference is the height. So we're gonna have height 1, height 2, and height 3. And then we're gonna define what our error is, which is that. So our set point minus the height of the third tank, and error is just the difference between it. But let me just do this next equation and kind of help explain what the significance is for that. So our inlet flow rate minus or equals the initial inlet flow rate plus the Kc value times E. And this equation right here kind of states that our inlet flow rate can be regulated, and because of the fact that we can manipulate this Kc value, we can manipulate our error by changing our set point. Right now we have set it to 1.2 or 20% above the steady state limit, I would say. And if we were to make it maybe 30%, it might increase or decrease however it affects it. And this will just regulate our inlet flow rate into the first tank. And then we're going to return with our dH over dt equation, which is just this right here for all three tanks. So, but instead of writing all of this, it's just Qn minus Q1, Q1 minus Q2, etc. So let's get to that, and then divide it by the area, and we're just going to Q1. I'm just gonna copy and paste. It's 2, it's 3. Oh, wrong one. It's 2. This is 1. Okay, and let's just shift enter. Nothing's wrong, so it's a good sign. And then from here, we're gonna our results equals. This is where solve IVP comes in, which is the initial value problem. We're gonna state our parameters. So we have our right hand side, which we defined above, and then we're going to define the duration period, which instead of writing 1000 we just do 10, and then np dot full, and this is essentially just saying for the 3 tanks the initial height is the same for all 3. And then method, which is redow. Hopefully I explained or pronounced that correctly. And then we have our dense output being true. If you put false, then it doesn't work, so we're not going to put it false. And then hplot res dot sol and tplot. And then we're going to have our h1 plot, h2 plot, h3 plot, and this is just going to allow us to see all 3 plots simultaneously rather than just one curve, or however it will show if we don't do that last line. But we want to see how all 3 tanks are being affected so we can compare and contrast that. And nothing's wrong, no errors, that's a good sign. So this code basically just this is it in terms of calculations and kind of the inner values or whatever. But it won't, if we run it, then it won't like show us the chart. It's just doing the value. So we can find the value. We don't have a visual representation, so this is where fig equals make underscore sub plot. Sorry, it's been a long night. It's like 11:42 right now. So yikes. Under scatter, and x equals t plot, y equals h1 plot, and the scatter is basically we're just defining our x-axis and y-axis, and this is going to apply to all three curves. So we're just going to show that okay, this is what the plot will look like. And then mode, we want lines, not like dots or something. And then name, we want to identify which curve is which. And then since Colab is so kind, it will just do the other three for us, so we don't have to keep doing that. And then we're going to update the layout because, well, let me just show what it looks like without it. It doesn't really look very presentable, kind of looks a little annoying. I don't really like looking at a white screen, to be honest. You can tell all of it. I just keep mine on dark mode. So we're going to change the layout. We're going to make it a little bit smaller. So what I've noticed is with 800 and height equals 400 is like a good sweet spot for me personally. I think I like that one. And then for the template, we want something a little bit more easy around the eyes. So Plotly Duck. And there we go. It looks a lot neater, not a lot nicer. Honestly, the colors pop a lot more. So we can see that this curve, it kind of just like smoothens out, I guess you could say. But let's see if we play around with this KC value and increase it, what happens. And I can see it's a little bit more divergent, and it's starting to not be as straight of a line towards the end. So let's try 0.7. Okay, well, it's diverging a lot now, so we don't want that. It's a little yucky, to be honest with you. So let's try 0.65. And it's still divergent, it's a little less, but it's not what we're looking for. Let's do 0.62. Yeah, it's pretty good. I mean, yeah, I think this would be fine. One thing I did notice when I was playing around with this is if you change the amount of time, it smoothens out quite a bit, and it kind of looks like the 0.61, but since we want to keep everything, I don't want to mess around with too many variables, we're going to keep it 0.6 and 1000, and it kind of looks, looks pretty decent. So with that said, I think our maximum, or actually let me go to our problem statement here. Essentially what we're looking for is the determining computationally the maximum value for the controller gain beyond which the liquid levels become unstable, and controller gain is this KC value. So we're looking for the maximum possible without divergent, or the oscillatory divergent, or diverging, whatever the term is there. And from the looks of it, even though we don't hit that like 6.12 mark, this is probably the best value in this scenario to play around with, unless you change up the HSP or air or whatever. I don't think it's gonna get any better than this. And in part B, we're gonna add an integral controller, so we'll see how that affects it. But this is only a proportional controller, so there's not many factors that can manipulate this. So 0.6 is the maximum for any diverging or any yucky stuff. So, yep. All right. See you in part B.